Okay, so welcome to Unit 3.2, Thermodynamics, Part 3 of 3. This is the last video for 3.2. So to recap, we'll start off by recapping Part 2. In Part 2, we learned about entropy, which measures disorder. We can think of it as measuring disorder. And we said that if disorder increases, delta S will also increase. And this is true for a spontaneous process. So if you want to increase the spontaneity of the process, you want to increase its disorder. We talked about the three ways to increase the entropy or disorder. One is phase changes, going from a solid to a liquid, liquid to a gas, or from a solid to aqueous. We also talked about increasing moles. So the more particles or pieces that you have, the more disorder it's going to be. It's sort of like if you only have 5 pieces of paper on your desk to organize, or 5 shoes in your closet, that's going to be more ordered than if you have 30 pieces of paper or 30 shoes. So the more stuff you have, the more disorder there's going to be. And so delta S would be positive. And finally, increasing space. The way I like to liken this is when if you have a messy desk, which is what I typically have, if I take all my papers and pile them onto one side there, I sort of decrease the space that's available to my papers, and so therefore I've increased the order, which is decreasing the disorder. So my desk becomes less disordered when I shove all my papers into one small space. But if, on the other hand, I let my paper spread out all over my desk, then that's going to be more disordered. So the more space you have, whether you do it by increasing volume or decreasing increasing volume or decreasing pressure, the more space that you have there, the more disorder you will have. And finally, we continued practicing heating curves. You created 2 of your own. So that's what we did in Part 2. All right. So let's go back to this idea of what drives a chemical or physical change. As we know, because we said this many times, that a chemical or physical change tends towards the lowest energy state, and that process will be spontaneous. It will happen on its own. You don't need to put any extra effort into it. And we looked at the 2 ways. In Part 1, we looked at enthalpy, so decreasing enthalpy or heat in a system increases spontaneity, and entropy is the opposite. Increasing the disorder will increase the spontaneity. But how do we sort of combine these 2 things? How do we quantify spontaneity with these 2 terms? It's sort of, they're kind of working in opposite, like enthalpy wants to decrease, entropy wants to increase. And we looked at an example with like the ice cream cone melting. So with an ice cream cone, as it's melting, enthalpy is increasing because you're putting heat into the ice cream cone into the ice cream in order for it to melt. But the disorder of that system, you're going from this solid substance to a liquid substance, the disorder is increasing. So, but overall the process is spontaneous. So what's going on there? How do we sort of predict that? And that's where this equation comes in. The delta G equals delta H minus T delta S. This is one of the most important equations that you should memorize. It should always be in the back of your mind. Maybe not right away, but you should really get used to thinking about this equation. So this is the equation we use to quantify spontaneity. And in this equation, delta G is Gibbs free energy. Delta H and delta S, you know, are change in entropy and enthalpy and entropy respectively. And so I want to first get started by, you'll learn more about what change in Gibbs free energy is later, but I want to first get started by talking about under what conditions would delta G be spontaneous. And one of the best ways of thinking about that is we know that for delta H, it should be negative in order for it to be spontaneous, and for delta S, it should be positive. So if we sort of like just plugged in those values into this equation, we can sort of make the prediction there. So I'm going to plug in a negative here for delta H and a positive for delta S. And so we have a negative number minus a positive number. Based on that, what do you think the sign is for delta G? The sign for delta G should be if it's spontaneous. Right, so if you have a negative number subtracted by a positive number, overall you're going to get a negative number. And so under spontaneous, when a reaction is spontaneous, delta G is going to be negative or less than 0. Okay, so let's sort of summarize that here. We can use the change in Gibbs free energy to quantify spontaneity, and essentially what I mean by that is the more negative the delta G, the more spontaneous the process is. So if you have a process that has a -5 delta G and one that has a +10, the one that has a -5 is more spontaneous than the one with the +10. One quick note is that G measures the maximum work a system can do, or Gibbs measures the maximum work a system can do. We're going to learn more about that later, but that's really just to say that delta G is not the change in energy. They're not the same exact things. Another thing to note here is that the delta G of the forward reaction equals to the negative negative delta G of the reverse. So that's just something, again, sort of to keep in the back of your mind. If you're given the delta G of the forward reaction is -12 kilojoules, then you know that the reverse reaction is going to be +12 kilojoules. Finally, again, this equation shows up all the time. Please make sure you memorize it. All right, so let's go through in terms of what the signs of delta G is. If it's negative, then it's spontaneous. If it's at if it's 0, that means it's at equilibrium. So that means the forward and the reverse reactions are equally spontaneous, and so delta G is 0 there. And then the last one is if it's greater than 0, it's positive, it's non-spontaneous. Okay, you should have this table in your note packet, and you want to make sure you find it. So we're going to fill this table out, and what we're going to do is we're really just going to focus on whatever the sign of delta H and delta S is. When is the reaction spontaneous? Is it always spontaneous? Sometimes? Under what conditions? And when I say conditions, I'm talking about the temperature here. And this is a sort of problem that we'll look at more at the problems in class, but AP style questions oftentimes have this on there. So we're just going to practice the skills that we need to sort of figure this out when something is spontaneous based on the sign of delta H and delta S. We've already done the first one. So we saw that when delta H is negative and delta S is positive, we can only have a negative delta S because a negative number subtracted by a positive number will only be negative. So delta G will always be negative, so the reaction will always be spontaneous. We're now going to look at the next case. So the question then becomes, can a process be spontaneous when delta H is positive and delta S is negative? So you can kind of approach this conceptually. We know that when delta H is negative, it's spontaneous. So when delta H is positive, that's non-spontaneous. For delta S, we know that when it's positive, it's spontaneous. So delta S is negative, non-spontaneous. So delta H positive and delta S negative, they're both non-spontaneous. So could there be any conditions where it's going to be spontaneous if they're both non-spontaneous? Probably not, but let's see how we can solve that mathematically. So here what we can do, the same thing we did before, is we can go ahead and plug in our sign. So we have a positive for delta H and a negative for delta S. And then when you have a positive number subtracted by a negative number, what happens? When you subtract a negative, this portion becomes positive. So based on that, could we ever have a negative delta G? No, we can't, because we have a positive combined with a positive, because remember, when you subtract negatives, become positive. And so delta G will always be positive. That means it will never be a negative. So in your chart there, what you're going to fill for the sign for delta H is positive, delta S is negative. And then for spontaneous, it's never going to be spontaneous. Delta G can never be negative in that case. And you can show your work by showing the signs here. Okay, so the next question is, now we're going to try it when they're both positive. So the thing is, when they're both positive, delta H is going to be non-spontaneous, but delta S will be spontaneous. So how can we get it so the whole thing is spontaneous? Again, we're going to go ahead and plug in our numbers or our signs. So taking a look at this, we have right now for delta H is positive and delta S is positive, a positive subtracted, remember this is a subtraction, subtracted by another positive. So what must be true in order for the whole thing to be negative? In order for the whole thing to be negative, this second positive must be bigger than the first. So that means this T delta S term must be a larger term. Now we can't change delta S, but we can change temperature, our T there. So if we're going to change T, do you want to increase T, have a large T, or have a small t in order to get the second term to be larger? Right, so in order for the T delta S to be greater than the delta H, we need the temperature to be high. We need to have it at a high temperature. That means that this, when delta H is positive and when delta S is positive, the whole thing can be spontaneous when when you have a high temperature. Okay, so now we're going to try that one more time, and this time we're going to try it where delta H is and delta S are both negative. So in this case, the delta H term is going to be spontaneous, and the delta S term is going to be non-spontaneous. So what must be true in order for the whole thing to be spontaneous? Under what conditions? So when we go ahead and plug things in, we get negative minus a negative. And if we want the whole thing to be negative, remember, a minus and a minus together will become a positive. That means we want this first negative to be bigger. So we want the delta H term to be bigger in this case. So what do you think must be true about the temperature? Right, so we want a low temperature in this case to make sure that this term is smaller, as small as possible. So in this case, delta G will be negative at a low temperature. And so here we can go ahead and just plug in this last thing into these last two things into our table here. So when both are positive, it's going to be spontaneous at a high temperature, and you can show your work here. And here, when both are negative, it's going to be spontaneous at a low temperature. Take a moment to get this chart filled in. Okay, last thing I want to do is just sort of recap sort of what we've done in this part 3. So, first thing we did was we learned to quantify spontaneity with Gibbs free energy. Remember, we had the delta H and the delta S terms, and sometimes they kind of worked in opposite. So how do we really quantify things being spontaneous? And that is through the Gibbs free energy. The more negative the delta G, the more spontaneous. The next thing we do was we looked at the Gibbs free energy equation, and we learned that it takes into account both the heat and the enthalpy, and so that's how we can use it to quantify spontaneity. We also predict the sign of delta G by knowing that delta H is negative and delta S is positive for spontaneous processes, or when delta H is negative and delta S is positive, they increase the spontaneity. So we know that delta G must be negative under the in order to be spontaneous. We also predicted conditions at which a process is spontaneous. So if delta H is positive and delta S is positive, for example, in order for it to be spontaneous, the temperature has to be high. All right, so the purpose of this video, of all three of these videos, just so you know, is not so that you know everything. It sort of gives you a preview so we can start tackling problems in the next class. So why don't you do a summary about what you learned today, what you're still confused about, and next steps to address your confusions. I hope you found this video helpful. Have a quality day.